Okay, just picking up where we left off here, I'm just going to kind of use this as a graphic organizer based on what I've already created. So remember, we're going to have something called an infinite, and that's so easy to see because it's going to be an asymptote, and I'll show you what that's going to look like. Then remember, we have jump, and jump really just occurs from a piecewise function. And then we're going to have a removable, and that is typically going to be from when factors cancel. And it looks like that pen is not working. So let me see if I can find us another pen. Here we go. This is when factors cancel. So, an infinite discontinuity, anytime you state a restriction, when you have something that looks like this, let's copy this down. And then let's say we already factored something, and we got these factors right here. So, if you notice, I know x cannot equal a positive 3 because it would make the equation undefined. It'd have 0 in the denominator. I also know that x cannot equal a negative 4. So if I was trying to graph this, I would for sure have two infinite discontinuities, and I'm just going to abbreviate discontinuity because I have two spots where this equation would be undefined. So remember, this is going to create that vertical line that's at the top of your paper. Now, real quick for piecewise, I won't go into too much detail, but what it is going to be some sort of line. Let's say y equals 3x. We'll just say we have something like that. And then I'll just try to actually match it as close, just spotting from this. So I know this is a parabola. Let's say that this is going to be y equals x squared plus 1. And then remember, it's only going to have a jump if I cut these off. So let's say I want this line right here, y equals 3x, but I only want it when my x values are less than, let's say 2. Let's say negative 2. So negative 2 is possibly where that gap is. But then if you notice, it picks up right here. So for the parabola, notice it's filled in. So I want my x values to be greater or equal to negative 2. And my outputs are going to be different. They're not going to be the same for sure. But if you notice, that's going to create that jump because of those y outputs, those values. All right, now let's talk about when factors cancel. So I'm actually going to go right back over here, and I'm going to change just the bottom by one term. Let's say instead of we had x minus 3 here, let's say we factored something and we got x plus 3. And then I am going to factor this numerator. I didn't factor this over here. I'm going to go ahead and factor this and see what we get. When we factor this, this is actually called a perfect square trinomial. It's going to be x plus 3 times x plus 3. So if you notice, I have two factors that cancel here. They're the same on the top and the bottom. So what happens anytime you have factors that cancel like this, you're going to have a whole, but it's called a removable. And it's always going to be at the opposite value, just like we did over here. So this says plus 3. So I know this is removable at x equals negative 3. But look, for this example, I still have one more discontinuity. Remember, x could not equal negative 4 over here. It would make it 0. Same thing. We also have an infinite at x equals -4, because remember, that's where it's going to equal 0. So back to kind of the whole full thing here, and I used red purposefully. So remember, an infinite discontinuity is most likely from a vertical asymptote, which would make the equation undefined. Notice I did not have any red in my graph, and I know that I didn't have any red in my graph because this is a jump discontinuity, usually created from a piecewise. And remember, instead of writing these two together, I could use my piecewise notation. And remember, I'm stating that the domain here has to be less than -2. That's why I have an open circle. But here it can be greater than or equal to a -2, I should say. Notice it's filled in. I didn't have any values that would make it undefined. That's why there's no red on my graph. However, over here, I did have a hole. Now, this example does not match this example down here. However, I just wanted to show you these two factors cancel. If I did graph this, I would have a big open hole where x equals -3, which is somewhere over here. And I would also have a vertical asymptote, which is an infinite discontinuity at where x equals -4. The last part is going to be end behavior. All right, so for end behavior, just like I started out drawing some graphs for discontinuity, I'm going to draw some graphs for some continuous functions, and we're going to analyze that end behavior first. So I'm actually going to draw 4. I'm just going to put one on top of the other. I have 2 columns here. So to discuss end behavior, it is really all about the arrows. So we are looking for how each of these graphs behave at the arrows after it's off the picture. So the first graph that I'm going to draw is going to be what is considered a positive graph, and I'll show you why. I'm going to draw something that kind of looks like the letter W. That is for sure a function. If I traced it, that is not a vertical line. It's increasing pretty steep, but that is not a vertical line. When I trace this, none of my x values repeat, and I know it's continuous because I would not have to lift up my pencil to draw this shape as I move from left to right on the coordinate grid. Let me show you another positive function. That is also considered a positive function. Now let me draw a couple of negatives, and maybe you can kind of start seeing why I'm calling these graphs that I'm about to draw negative. All right, so those are for sure negative functions down here. These are 100% positive functions up here. And the reason why I know that, it is so simple. I just know because of the arrow on the right side. Always the arrow on the right side. If you have an arrow that is up on the right, that function is positive. There is a positive leading coefficient there. Same for this. They are both positive for sure because I have an arrow up on the right side of my picture. Now, if I have arrow down on the right, still analyzing on the right, then I know the function is starting with a negative. So it has a negative leading coefficient. one more thing before we start talking about end behavior. So not only can functions be positive or negative, they could also be even or odd. And I know we talked about that earlier when we were discussing symmetry. Now again, I know for sure that we are going to have an even based on the arrows. I know we're going to have an odd based on the arrows. So if you notice, both of my arrows are pointing in the same direction for this first graph. My arrows here are pointing in opposite directions. So if you have arrows in opposite directions, then that is considered an odd function. Now, I'm not saying it is necessarily symmetric around the origin. I just know that this function is odd because the arrows are in opposite directions. One more is going to be an even function. An even function has arrows pointing in the same direction. Anytime I see two arrows pointing down or two arrows pointing up, that is an even function. Okay, so let's start hopping into end behavior. So remember, for end behavior, it's all about the arrows, and we scan it like a graph from left to right. So the first thing I see is an arrow. Arrow means infinity, and this is the negative infinity part of the x-axis. So as my x values continue to go up, they're also getting lower and lower and lower. So as my x approaches negative infinity, then this function is going higher and higher and higher. So the lower my outputs, the lower my inputs, the higher my outputs. So that's approaching positive infinity on the left arrow. As my inputs get bigger over here, oops, that is an infinity symbol. So do my outputs. So this is also approaching positive infinity. And remember, that is an infinity symbol. I'm going to make that cleaner on the PDF that I'm loading. That's an infinity symbol. All right, so left arrow's going up. Positive outputs, positive inputs. What you need to notice here is this function's outputs both are going up, up, up. Same end behavior. So if the arrows are pointing the same, it's an even function. Now we get to add something else to this. They are going to have the same end behavior. All right, let's analyze the opposite. Over here, this is a negative infinity arrow, so as x approaches negative infinity, I know it's negative infinity because it's to the left of the origin. What's happening to my outputs? Well, as my x values get lower and lower this way, my outputs are getting lower and lower down. So as x approaches negative infinity, so does f of x. Let's look at the right side. Right arrow right here. So as x approaches positive infinity, so do the outputs. So if you notice here, these do not match. And if it's an odd function, they never will. So now we get to add more info about this odd function. So opposite end behavior, opposite arrows are always going to give you opposite end behavior. And that's going to be the same for negative functions right here. Look, As x approaches negative infinity, here's my left side arrow, f of x is approaching negative infinity. However, on the right side, if my outputs get larger over here, if my inputs get larger over here, my outputs are still getting smaller. See how they have this same end behavior for the outputs. No matter if they're getting larger or smaller as inputs, the outputs are always getting smaller. All right, over here, as x approaches negative infinity, look, this time it's flipped. As my inputs get smaller and smaller and smaller, my outputs are getting bigger. So this is approaching positive infinity. Over there on the right side arrow, remember the right side arrow is positive infinity. Let's take a look at what's happening to those outputs. It's going down. So as my inputs get larger, my outputs are getting smaller. Notice these end behaviors for the outputs are opposite. And that is going to be a brief introduction into end behavior.